Good morning. In this section, we're going to look at a particular type of application where you have some sort of situation where two things are changing and the rate at which one changes affected the rate at which the other thing changes. As an example that we're actually going to go through step by step, imagine pumping air into a ball so that the volume of the ball is changing at a certain rate. Well, the diameter of the ball, how fast that's increasing, will be affected by how fast you are changing the volume of the ball. So those two are related rates. The tool that we're going to use to solve these problems is going to be the chain rule. So let's go through a couple of examples so you see how this process works. So let's say air is pumped into a ball. And that the volume increases at a rate of 100 centimeters cubed per second. How fast is the radius increasing when the diameter is 50 centimeters. So the other thing to think about is with this ball, as you're pumping more and more air in, at the same rate, will the diameter, in addition to the radius, will that increase slower, faster, or at the same rate? What do you think? Well, let's take a look. Let's see if we get something that tells us, well, actually, it doesn't even matter what the particular time is, but the radius is increasing at the same rate. Or maybe we'll see that it's actually different depending on how much air is in the ball. So how do we solve this? Well, let's write down what information we have. Let's mathematize this question, converting it into some sort of symbolic notation, and finally an equation. So air is pumped into a ball. I could care less that it's a ball. The volume increases at this rate. So notationally, we could express this as dV dt is equal to 100. So I'm using Leibniz notation here because it helps me see what's going on very explicitly. How fast is the radius increasing? So I'm looking for dr dt. I don't know what that is. When the diameter is 50 centimeters. Well, I could write d equals 50, but I see that I'm living in the world of r, so I'm going to write this. I'm going to write r equals 25. So I want this. When this is happening, that's true. So again, the rate at which these guys are, their rates are actually related to each other. So the question is, how do I take advantage of that relationship between the two? Well, I could do that because I know that volume is 4/3 pi r cubed. And I call this a static relationship. So it's okay if you forgot that formula for the volume, but I think everybody knows that there's a volume of a sphere lurking out there somewhere, and this is the volume formula. It's static because this is for a given r and a given v. So if r is 10 cubed times pi times 4/3 gives me my v. In this situation, though, r is changing. The ball is being pumped up. So instead of an r, I should really be thinking of this as an r of t. It's a function of time. Over time, the radius increases. So the right hand to this equation should really be written as 4/3 pi r of t cubed. Now, I don't know what that r of t function is, but I know that I can write it as r of t. In addition, if this is now r of t, then v is no longer static. V is going to also change with respect to time. So the left-hand side becomes v of t. Again, I don't know what the v of t function is, but I know it exists out there somewhere. So these are two abstract representations of the processes behind the scenes. And we know that this relationship is true because for any given point it's true. And I call this the dynamic relationship between the two quantities. Well, how does that help me? Well, I know this, and I'm looking for this. This relates v of t and r of t. Well, if I now take the derivative of both sides, won't I have a dv dt in there somewhere? Yeah, I will. Well, I have a dv dt, taking the derivative of both sides, is 4/3 pi. Let me take the derivative of r of t cubed. Or I invite you to pause the video and see if you can take the derivative of r of t cubed. Hopefully you said, oh, that's 3 r of t squared, but we have to remember the chain rule and multiply by the derivative of the inside. What's the derivative of the inside? It's just dr dt. So again, I don't know what my r of t function is, but it doesn't matter. This will be a true statement by the chain rule. Okay, let's see if that helped answer the question. Well, I know dv dt is 100. And r of t is, well, r of t is a function I don't know, but I'm asking this question at the point in time when r is 25. So this is really asking me to answer this question at one specific point in time, and at that point in time, my r of t is 25. Times dr dt, which I don't know. And it looks like I have enough information to solve this question. So what I'd like to do is cancel these guys. And yeah, let me simplify this. I want to make a point about something. So this is the same thing as dividing by pi times 25 squared, and I guess we could also divide by the 4 here. So that's what dr dt is. So I know I can simplify that, but I want to leave it in that form to make a point. So what point do I want to make? As the radius increases, so as we move forward in time and the radius is increasing, this denominator is going to get bigger and bigger and bigger. The numerator stays the same because this rate stays the same. Since the denominator is getting bigger and bigger, pause the video and say in words or explain what happens to the rate of change of the radius as the radius gets larger. Right, hopefully you said, well, as the radius gets larger, the denominator is going to get bigger, this fraction is going to get smaller. So as the radius increases, the rate at which the radius is changing is going to decrease. All right, so let's kind of step back for a second then and see how we solved this one. Just like optimization and modeling type problems, the only way to get better at these things is to solve them, but there is a process behind the scenes. So the first step is mathematize. So you want to convert things into symbolic forms. Once you do that, you want to find a static relationship between the two variables. There's always one lurking about. You got to find it. So here, my variables are v and r. They're related by the volume formula. Third, convert it to a dynamic relationship. Fourth, take the derivative. And then finally, plug in and solve. A couple of points that I would like to make about this. First, students are tempted to set things equal to 0 because we've been doing that all quarter. Nothing about that in this type of problem. We're not trying to minimize or maximize anything. Second, students like to try to take the 25 over here and plug it in over here in the static version. Well, that's not going to help us because that's just telling us information at a single point, and it's just giving us the volume there. There's no way we're then going to be able to find dv dt. We need v to be a function of t first to be able to use this information in solving the problem. So this was an example of a related rates problem where you have two quantities which are changing and they're related somehow. And this is the method by which you will be able to solve these problems, again, through lots of practice. So thanks for listening. I hope you enjoyed the lecture, and I will see you next time.